Welcome to the solution of problem 2 for A. Just want to give a quick shout out to Kristoffer in the beginning of this video as a thank you for providing me with a good way to explain this exercise. So this is a new version of the solution which will replace the old version of the solution because I prefer this version. So what we want to do in problem 2 for A is to find the density of the unconditional loss X, where X is the total damage done to the house you have in the Caribbean as a result of a storm approaching, which will have either strength 1 or 2 or 3. So this is actually one of the first exercises where you are looking at two random variables next to each other. We have the storm strength N and we have the total loss X. And what we want to find is the distribution of the total unconditional loss X. Now let's first think a little bit about, well, what we want is actually to find the density, right? But what do we know about X? Well, we know that given n is equal to 1, X has this distribution. Given n equal to, X has this distribution. And given that n is equal to 3, X has this distribution. So in some way, we want to take these conditioning things into play. And how do we do that? Well, first of all, it's a bit more intuitive to work with distribution functions instead of densities. So just recall for a moment here that the density of a distribution, so the density fx of x with lowercase f is the derivative of the distribution function. Uppercase F, x of x. So the little x is the value that we evaluate the functions in, and the capital X just stands for that we are looking at the distribution of the random variable x. So what we're going to do instead of finding the density is we're going to try to find an expression for the distribution function first. Now, first of all, just before we really get started, let's just take a look at this intuitively. Intuitively, we know that the storm can be of 3 different strengths with probability P1 and P2 and P3 respectively. And in each of these cases, X will have different distributions. So we can already now kind of expect that the distribution function of X is just P1 multiplied by the distribution function in the first case, plus P2 multiplied by the distribution function in the second case, plus P3 multiplied by the distribution function in the third case, right? Because the distribution function can be 3 different things depending on the storm strength, and our best guess for what the total distribution function is would just be taking a weighted average of those 3 conditional distribution functions. So that's just the intuitive guessing here. Let's take a look at the calculations. So what we want to find in our first step is the probability that x is smaller than or equal to some value x, where we just say let x be greater than 0, since we're not interested in the negative values of x. So let x be greater than 0, then we have this. Okay, and how can we go on? So we want to bring n into play. And the way we do that is by recalling that the probability that n is either 1 or 2 or 3 is 1, because this is the entire sample space. So we can recall from SS that if you have any event, A, and you intersect it with the entire sample space. I don't remember if you called it E or S or the universe or omega, kind of depends on your notation, but if you just intersect it with the entire universe or sample space, then what you get is just A again, right? Because if this is the entire sample space and you have A in here, when you intersect it, you just get A again. So what we can do is we can intersect the event that x is smaller than or equal to little x with the event here, which takes up the entire sample space. And the next thing that we can do, well, we want to get to some point where we have n equal 1, n equals 2, n equals 3. So the next thing we can do is to recall that, well, the three events n equal 1, n equal 2, n equal 3 are disjoint. So that means I can split this up into the sum of three probabilities. So the probability of x being smaller than or equal to x and n equal 1 plus probability of x being smaller than or equal to x and n equal 2 plus the probability, just go down to the next line here, plus the probability that x is smaller than or equal to x and n is equal to 3. So how can I continue now? Well, the next part here comes from a little definition that you all should be able to recall, namely that, well, we know that what we have here is the probability of an intersection of two events. And what we want is somewhere where we can use the probability of x given something else. So we want some conditional probabilities here. And we can recall that the probability of one event given another event is equal to the probability of their intersection divided by the probability of whatever event we condition on. So that means that if I want to plug in the conditional probability here instead of this probability of the intersection, then what I can do is I can multiply this thing over on this side and I have the expression I want. So what we have now is that this thing is equal to probability that x is smaller than equal to little x given n equals 1 multiplied by the probability of what we condition on, which is n equals to 1, plus probability that x is smaller than or equal to little x given n equal 2 multiplied by the probability that n is equal to 2, plus the probability that x is smaller than or equal to x given n is equal 3 multiplied by the probability that n is equal to 3. Okay, next part. So what I'm going to do now is introduce you guys to the notation that you see in Formula 412, and that is on page 41 in the book. So Formula 412, page 41 in the book. Essentially, you can just use that formula or the formula below that to solve this exercise. Essentially, you can just use formula 413 to solve this exercise. But because the notation in both formulas are actually kind of confusing, I would just like to explain to you guys what that notation is about. So what we have here is the conditional distribution of x given that n is equal to 1. So the conditional distribution function of x given that n is equal to 1. So there's another notation for that which is used in 412 in the book, and that is written as, so capital F for distribution function, subscript x given n, because what we're looking at is the conditional distribution function of x given n, and then parenthesis little x, because that's what we evaluate the conditional distribution function in, and then given 1, because this means conditional distribution function of x given n equals 1, evaluated in little x. Okay, and then we have the point probability of n equals 1, and that was just P1. And I can kind of continue that with my new notation here. So the conditional distribution function of x given n equal to evaluated in little x multiplied by p2 plus the conditional distribution function of x given n equals 3 evaluated in x multiplied by the probability of the storm being of strength 3. So we can write this up like this here, and what we have in conclusion now is that the unconditional distribution function, so let's just write here, hence the unconditional distribution function of x is equal to the sum of conditional distribution function, so of the conditional distribution function of x given n equal to n evaluated in x, where n can be 1, 2, and 3, and then each weighted with the probability of that conditional distribution function coming into play. So this is the unconditional distribution function of x. So how do we find the unconditional density function of x? Well, as we recalled before, the density is just the derivative of the distribution function. So hence, by differentiating on both sides with respect to x, we see that the unconditional density is just equal to the derivative of the sum of the weighted average of conditional distribution functions and we can take the derivative inside the sum, pass the constant, and what we have here is just the derivative of the conditional distribution functions. So the derivative of the conditional distribution function is equal to the conditional density function. So let's just write that out here for good measure. The derivative of the conditional distribution function of x given n is equal to some value n is just equal to the conditional density of x given that n is equal to some value n. So hence the conditional density is equal to, hence the unconditional density is just equal to the weighted average of the conditional densities. And what are the conditional densities? Well, we know that in each of the conditional distributions for x, where n is equal to 1, 2, and 3 respectively, the densities are those of the exponential distribution with parameters lambda 1, 2, and 3 respectively. And in the book, they give us the exponential density function. So what we can do is we can just plug in the value of the density function in for the exponential distribution, and then we're done. So the total density for x is given by the sum of Pn multiplied by lambda n multiplied by e to the minus lambda n multiplied by x for n equals 1, 2, and 3. And this is the answer. And not surprisingly so, because what we've just reached as a conclusion is just that the density of the unconditional loss is equal to taking each of the conditional densities. So each of the conditional densities for lambda, for case 1, this will be lambda 1, e to the minus lambda 1. So we just take each of the conditional densities and multiply them by the probability that that will be the density that we will use for x. Because with probability p1, the density will be lambda 1 multiplied by e to the minus lambda 1x, and so on and so on. So intuitively, this makes a lot of sense, and now this also makes sense theoretically. What we actually have here is a mixture distribution, which is part of Chapter 4 curriculum. We will get back to that later, so no worries.